Hey guys, so I decided to create this video on galvanic versus electrolytic. How do I start? Because I've seen a lot of people ask different questions that make me kind of concerned about how do I put all this together. So far we've done galvanic cells and just the multiple choice and free response dealing with it. We've done just electrolytic cells, free response and multiple choice dealing with it. Well, when you take your unit test, you're going to have everything meshed together. So I think it's very important for us to not get these confused and mixed up, and to be able to compartmentalize the differences between them, but then also look at a big picture to figure out how can I distinguish one from the other. And so that's what this video is about. It's very important to watch it before your test, maybe before your practice test as well. So galvanic versus electrolytic, what are the main differences between them? Well, galvanic cells are thermodynamically favorable. Remember what that means. That means that the reaction happens on its own. I just put these substances in here, hook up my cell, and the reaction automatically occurs. Your electrolytic cells, on the other hand, are thermodynamically unfavorable. So what that means is I have to hook up some sort of external power source, whether it be a battery or something of that sort. An electric current, a battery, something of that nature is a power source that's hooked up to this. And that power source is going to push electrons through here and make this reaction occur. And so that's what happens when reaction, in this case, is thermodynamically unfavorable. Now, due to the fact that these are favorable and unfavorable, they get certain sign conventions. So for thermodynamically favorable, which is all galvanic cells, we have positive E cell values, negative delta G values, and K values that are greater than 1. And so what K stands for, we haven't talked about it much, is equilibrium constant. It's just a relationship between your products and reactants to let you know if the reaction is thermodynamically favorable or not. So if you ever see any K quantity that is greater than 1, then that means this is true. If you were ever to see any K value that is less than 1, then that means these things are true. So you see how these sign conventions between electrolytic and galvanic are different. So thermodynamically unfavorable is a negative E cell, a positive delta G, and a K value less than 1. So this is true for all electrolytic cells. This is true for all galvanic cells. So that's as far as sign conventions go and the conceptual thing of like what's happening. Now let's talk about the differences between if they were to give us a picture of an electrolytic versus galvanic. Because you've noticed that a lot of your free response problems, they'll show you the picture of the cell and ask you questions about that. So if I see a galvanic cell, my picture will have two separate containers, okay? And so there's a half cell working on this side and a half cell working on this side. And together, these electrodes are hooked up. Now, this is not a power source that you see here. This is a voltmeter. So that is just reading your voltage that you get based upon the reaction. You also have one extra thing in here that is necessary in order for the cell to actually operate, and that is your salt bridge. Remember that your salt bridge is there to balance out the charges that are building up in the solution. Your anions are going to your anode, and your cations of the salt bridge are going to the, your cations are going to your cathode, your anions are going to your anode. And so make sure that you are able to talk about the conceptual things here. So if I see a picture that has a salt bridge, has two separate containers, that automatically lets me know that I'm working with a galvanic cell. Let's see how that's different from an electrolytic cell. An electrolytic cell does not have two separate containers. There's only one container that this is occurring in, and you don't see a salt bridge. A salt bridge is not necessary for an electrolytic cell. You will also definitely see a power source that's applied to your electrolytic cells. That is necessary in order to get the reaction to actually happen here. So we could see a picture form. We could be discussing whether it's thermodynamically favorable or AKA spontaneous versus thermodynamically unfavorable, aka non-spontaneous. So that's another thing that they could talk about in the problem. They could just say, hey, you have a galvanic cell that blah, blah, blah. that lets me know that I'm working with this, and they could say you have an electrolytic cell that works with, you know you're working with this then. They could also give you some keyword hints like an electric current is passed through. That would tell me that I'm working with a power source, so it's an electrolytic. A battery is hooked up to, so that lets me know that that's a power source applied, and so we have an electrolytic cell there as well. So there's lots of different little keywords, pictures, and sign conventions that can help us distinguish between the two. Well, now what we want to do is talk about how do we start it. If we can now pick apart that I have a galvanic versus an electrolytic cell, how do I start them? Because how I start the question is a little bit different of a mindset than other things. So if I have a galvanic cell and I've identified that I'm working with that, the very first thing that I have to do is look at my half reactions. And so that is by using the standard reduction potential chart. Remember that you don't have to use this chart for the test. That doesn't mean you have to memorize them, but they will give it to you in a smaller data table format. So you don't have to look through 90 million and try to find it on here. So very first thing, after I identify it's a galvanic, I look at my half reactions. And when I look at my half reactions, I'm looking for the thing that is more positive in value. The more positive value is always reduced. So if I have to start by writing a reaction, if I know that the species that is more positive is reduced, I'm going to have to start with that species in solution. And so that is going to be my aqueous thing in the reactant side, and it's going to be my solid thing in the product side. So that is going to be for my reduced species. If I am looking at my oxidized species, that species is going to be my solid on the reactant side and going to be my aqueous thing on my product side. And if this that I have written here doesn't make sense to you, make sure you look at my key that's dealing with the free response questions for galvanic cells, and hopefully that will make more sense in a more detailed format, okay? So, galvanic cells, very first thing I do is look at that half reaction. If I can look at my half reaction and figure out who's reduced, and then write my entire reaction from there, I can answer any of the other questions that they ask. Let's talk about electrolytic now. How I start and approach my problem different? Well, for electrolytic, I am not going to look at my half reactions immediately. Instead, I am going to look at whatever solution is present here. I am going to look at the molten thing or aqueous thing. Now remember, there's different rules if it's molten or if it's aqueous. So let's give an example for this. Let's say that we have copper 2 sulfate that is present here in solution, and that copper 2 sulfate is aqueous. So what we do, we don't look at half reactions yet. We're going to save that for later on in the problem. We are going to immediately identify the solution and then ask ourselves, is this molten or is this aqueous? In this case, we have an aqueous solution. So we have to remember those rules for the aqueous. If my cation, so the normal rule is cations are always reduced, anions are always oxidized. That also applies if it's aqueous, but we have to pay attention to see what our cation and anion are. So my cation would normally reduce. Copper is not a group 1 or group 2, so that means copper will actually be reduced. And so I will see that reaction, Cu2 plus 2 electrons yields Cu solid. So this would be my reduced species. My cation is always reduced. Now, I look at my anion. My anion here is sulfate. So sulfate is a polyatomic ion. So sulfate will not be the species that is oxidized. Instead, water will be oxidized. So my half reaction for my oxidized species is going to be this half reaction here, dealing with water breaking up into oxygen gas. Now again, you do not have to memorize these equations. It's good to know that when water is reduced, it always forms hydrogen gas. And when water is oxidized, it always forms oxygen gas. That is one thing that I would recommend for you to know, and then you can pick apart the half reactions from there. So this is how I begin electrolytic cells. Once I identify who's reduced and who's oxidized, I can go into writing the equation, I can go into calculating my E cell and all of that things. Now, things that are not different between galvanic and electrolytic cells. Reduction still occurs at the cathode. Oxidation still occurs at the anode. That does not change. Your electrons do not change. They always flow anode to cathode. Doesn't matter which cell you're working with. The way you calculate E cell, reduced minus oxidized, that does not change. The only difference is that I'm not looking at more positive values for electrolytic. I have to figure out who's oxidized and reduced based upon these rules. Here, more positive is reduced. Here, doesn't matter, okay? Make sure you get that straight in your head. I still calculate delta G the same way, negative infi. If I were to do the Nernst equation, I still work it the same way. There are some extra calculations dealing with electrolytic cells, and that's your Q equals IT or I equals Q over T calculations where you have to do dimensional analysis. They love to ask those questions, so make sure you know how to do it. I hope this was helpful. I hope that this is able to kind of like separate the two, but then bring them together as a big picture. And let me know if you have any other questions dealing with that. Bye.